Chapter 15, number 34. A 3.2 kilogram balloon is filled with helium whose density is 0.179 kilograms per meter cubed. If the balloon is a sphere with radius of 4.9 meters, what is the maximum weight it can lift? So we'll need, as always, a picture. So there's our balloon with a mass m sub b, and hanging from it is the mass it's lifting, which I'll call m sub l. And then what we'll want to add onto that is a free body diagram, so we have something like this, where here we can treat the balloon and the lift mass as one combined object whose mass is mb plus ml, and then we feel the earth pulling down with F sub g and the air pushing up with F sub b. And what we want is to make sure that this is at worst neutrally buoyant, that the weight is smaller than or equal to the buoyant force, because what we really want to say is that the sum of the forces in the y direction should be 0. This is Newton's second law. And the sum of the forces in the y direction are going to be the buoyant force upward minus the weight downward. That's from the free body diagram. So we can say, let's see, we want the maximum weight it can lift. So we really want to just find Fg. That's interesting. All right, so Fg is going to be Fb, which is the density of the air. And we need to be careful about that because it's the air that's holding it up, even though they gave us a different density, right? They gave us the density of helium. That isn't directly relevant at this moment. Anyway, Fb is going to be rho times g times the volume of displaced air. So, well, we'll leave that in for a moment, but we know, I guess we can put geometrically that we know that the volume of a sphere is 4/3 pi r cubed. That's a geometric result. You're not expected to remember that. It will be on the equation sheet, but it's pretty standard and has been known for, 3,000 years. So we can stick with it. And then maybe we want to say, well, that's the total weight on the balloon plus the thing it's lifting, but that comes from two places, right? Because that's the mass of the thing we're lifting times g, but it's also the mass of the helium, of the balloon and the helium times g. They don't tell us what the balloon itself weighs, but even if the balloon were considered to be massless, the helium has a given density, so it is not massless, and we should put it in. But that's easy enough because that's just going to be rho of helium times g, right, times the volume of the balloon times g. And then this is actually what they ask, how much weight can we lift? So going over here, we can say that, putting these together, that the thing we want, ml times g, plus the density of helium times g times v, equals the mass of air times g times v. So the amount of weight that we can lift is actually the density of air times g times v minus the density of helium times g times v. We can factor that a little bit and say the amount that you can lift depends on the difference in the densities times g times v. And then it's just a matter of putting in some numbers. Not particularly great boards management here, my apologies. So we'll go all the way over here and say it's going to be the density of air. According to table 15.1 in your textbook on page 503, the density of air is 1.29 kilogram per meter cubed. And they tell us the density of helium is considerably less than that, actually, 1.179 kilogram per meter cubed. And then g, of course, is our standard 9.181 meters per second square. And then the volume, put in a different color just to highlight a little here, is 4 pi over 3 times the radius cubed, and the radius was 4.9 meters. Pretty big balloon, kind of like a weather balloon. And then we cube it. And all of those are known, so we can throw them in a calculator. And we get 5,371 newtons, which, based on our sig figs, are, well, we only have 2 digits of sig fig, So it becomes 5,300 newtons, or about 500 kilograms. More like 540, but something like that.